I find eigendecomposition to be one of the most fascinating, thought-provoking, sometimes weird, but also interesting and useful aspects of linear algebra. So I really enjoyed writing this chapter, and I particularly enjoyed devising all of these exercises for you to increase your knowledge of eigendecomposition and other related concepts like the matrix inverse and the null space and so on. So I hope you enjoy working through the exercises in chapter 13. Let me start this set of videos with exercise 1. So exercise 1 is about the eigenvectors and eigenvalues of the inverse of a matrix. Now, of course, a matrix has an inverse only if it's square and full rank. But that is fine for here because, with eigendecomposition, we are only considering square matrices anyway. So this problem is really just limited to full rank matrices that have an inverse. So the claim here is that the eigenvectors of A inverse are the same as the eigenvectors of A, and the eigenvalues of A inverse are almost the same as the eigenvalues of A, except that they are also inverted. So A and A inverse have the same eigenvectors, and their eigenvalues are just reciprocals of each other. So that's a curious feature of eigendecomposition and the matrix inverse. And I ask you to do two things here. First is to prove this, and second is to illustrate it empirically with a random numbers 5 by 5 matrix. Okay, so now I'll walk you through both. The proof is actually really straightforward. You know, this word proof has a lot of negative connotations in mathematics, and to be sure, there are plenty of proofs in math that are hard, that are like, they take a really long time and they're totally counterintuitive. But, you know, one of the things that I like about linear algebra is that a lot of the proofs in linear algebra are short, succinct, and beautiful and elegant. So let me start by showing you the proof. Here's the whole proof right here. It's really simple. So we have A equals V lambda V inverse. So here I'm just writing out the diagonalization of matrix A. And then I take A inverse, and now whatever you do to one side of the equation, you have to do to the other side of the equation. So I take the eigendecomposition of A and invert that whole thing. And then we just use the live evil rule to expand out these three matrices. So the first matrix is V inverse inverse, which is just V. And then we have lambda inverse, and then we have V inverse, and that's this V inverse here. And then what you can see is that the right-hand side of the equation is basically identical to the right-hand side of the equation here for A, except that we have lambda inverse in the middle. So that's the proof. It's pretty nice and simple. Okay, and here is the empirical demonstration to build intuition and yeah, just to see it in practice in real numbers. So here I create a random numbers matrix. Now, I'm forcing this to be symmetric, and this doesn't need to be symmetric. This is a perfectly valid square full rank matrix. We can compute its inverse, we can take its eigendecomposition, but the thing about random numbers matrices is that they are likely to have eigenvectors and eigenvalues that are complex valued. Now, perfectly fine, there's nothing wrong with complex valued solutions, but they're just a little bit harder to look at and to interpret from a kind of, yeah, it's just for convenience, I'm making this a little bit easier by forcing this matrix to be symmetric. And as I explained earlier in this chapter, a symmetric matrix is guaranteed to have real valued solutions, so real valued eigenvectors and eigenvalues. So again, just, just for convenience to keep this thing symmetric. Okay, here I take its inverse. Here I find the eigenvalues, and then I compare them. Okay, so that part is pretty straightforward. So we see here are the eigenvalues of A, the eigenvalues of the inverse of A. And now, again, we don't expect these two to be identical. We expect the eigenvalues of A, to be equal to the reciprocal of the eigenvalues of the inverse of A. And you can see that here I'm just saying 1 divided by. And here is just a little tip to sort the eigenvalues, they're not guaranteed to come out sorted. So if you don't have this sorting code in here, you might actually look at this and think that these two are not the same because they might be the same numbers but in a different order. But yeah, the order of the eigenvalues is arbitrary. Okay, so that is a pretty neat property of the matrix inverse and eigendecomposition. You might have noticed that I don't actually demonstrate the equality of the eigenvectors in this code here. That's certainly something I would encourage you to do. So you can also, so here I only extracted the eigenvalues. You can also extract the eigenvectors. Just make sure when you're doing that, that if the eigenvalues are not sorted in the same way for A and A inverse, then the eigenvectors are not going to be sorted in the same way. So it's a good idea to sort the eigenvalues, and you will also need to sort the columns in the eigenvectors matrix according to the sorting for here and the sorting for not the eigenvalues of A inverse, but sorting for the reciprocal of the eigenvalues of A inverse.